These videos are part of a course on food physics, of which this series belongs to the modeling section. Problem formulation is part of modeling, where we go from a physical world to its math model that consists of equations. There are 7 parts in this series on problem formulation, and they're about the details of problem formulation, the various steps. The first video is simply an introduction. These videos are organized in a way that the learner can stop and apply the principles to his or her own model before moving on to the next step. We start from the big picture showing the steps in a modeling project copied from a previous video. The very first step, we take a food process and write the governing equations and boundary conditions describing the process. That is my problem formulation. Next, these equations need to be solved, and typically they're solved by implementing the model in a software. So that's the next step. Then as we get model output, those need to be validated, and typically against experimental data. Once we have the model validated, then we run the model for many different scenarios for doing what if cases, and that is called the sensitivity analysis. Finally, with all this information that we developed, from there we have to distill the critical information and communicate these to others in speeding up the design and the design of a product or a process. So we make written reports or oral presentations. So this video is about the first part, that is the problem formulation, and there are separate videos for all the other steps. So this series of videos is only about the problem formulation. So here are the learning outcomes as to what we will be able to do when we are done with this series of videos. First, we should be able to break down the problem formulation into the major steps. Next is we develop the ability to consider competing choices in problem formulation steps. And finally, apply each step of the problem formulation to formulate the problem for a reasonably complex project. So those are what we should be able to do after we complete this series of videos. Now, you may have seen this quote in other places. As we start to formulate a physical problem into a mathematical one, the golden rule is to include only the physics absolutely necessary. So here is an example of what we mean by problem formulation. So if we take a physical process, let's say a deep frying process, problem formulation replaces this physical process by its mathematical equivalent. And that mathematical equivalent is made up of several steps. So for example, what is the goal, but also schematic like this one, and the governing equations that may look like this, or the boundary conditions, initial conditions, and properties and parameters. So once we have defined these, then the physical process here is completely replaced by this model, and after that, we can simply work on this model on the computer, and we hope to replicate what goes on in the real world. Restating previous slides, in modeling, we take a real physical process like frying and replace that with its mathematical equivalent, which are a number of equations, and then those equations are programmed in a computer to be solved. That is our computer model. And problem formulation refers to the replacement of the real physical process with its mathematical equivalent. Now, this problem formulation stage is critical because it introduces errors and uncertainties that will stay with the model. So, by far, the largest error that we introduce is due to the approximation of reality. But we also introduce uncertainties. And one of the obvious ones that we introduce is uncertainty due to variability and natural variability, natural biological variability. For example, if we are using potato properties in a model, then not all potatoes will, of course, have the same property. And so it is very important to be aware of this uncertainty in the model. Another type of uncertainty that we introduce is knowledge uncertainty. It's basically just things we do not know. What we think of the underlying physics may not be so. We do not know any better, so we go with what we know, but we need to be aware of this important limitation. Note that this type of uncertainty is not error due to known approximations. This has to do with what is completely unknown. The errors that we make and the uncertainties that we introduce in the problem formulation stay with us till the end. It is very important to see that by solving these equations exactly, even if we could possibly do that, we would still not get rid of these errors and uncertainties. So by reducing the error in computer model to zero, it does not get rid of these errors and uncertainties. So this makes problem formulation often the most critical step. Once the problem is formulated in terms of these governing equation and boundary conditions, of course, we talk about the solution to these equations. Solution of these equations, that is the formulated problem, is largely automated these days with the software available. So the good news is you often do not need to know as much math, and you certainly do not need to spend as much time like in the past when we had to write code from scratch. So those are the good news. Will not be doing the mathematical details. But there is also the bad news. And the first one I want to share is we have to remember that the software is just an equation solver. It has nothing to do with the particular physics, the particular problem, that the physical problem that you are trying to solve. It doesn't know the physical problems. It's simply solving the equations that you provide. If we do not formulate correctly, correctly in the problem formulation stage, that's here, the computation may be too hard, or we might have thrown out some important physics. Okay, so all that will not be caught in the solution stage. And almost always, you know, we have to tweak the solution parameters to make it easier for the computer to solve. So at this early stage, it is important to know that we can't just define the our model, our formulated problem any way we want, and all we have to do is click the run and we will get a solution. It doesn't work most of the time, so we have to make sure that we formulate the problem in a way that is a bit easier for the computer to solve. Here is a very conceptual graph, not to be taken quantitatively, of the time and effort needed in various stages of modeling process in the past and compared to that now. And the primary point to make here is it is the solution process that has been affected the most with all the developments in computing. In the past, we would have to code in this process from scratch, whereas now almost always we use an available software. But problem formulation, on the other hand, is still manual and requires background and insight into the physics. This has not been automated. Now, problem formulation is easier today because of the different modeling frameworks that have already been established, but as we end up doing more and more complex problems relative to the past, they end up taking about the same time and effort. Of course, all this depends on the type of physics that we are talking about. The main point here being that problem formulation is a process done manually and it takes time. It is not to be confused with all the advancements in the computing. So we are balancing between the level of details and the time it takes to solve. So on one hand, we could simplify too much that does not address the goal, and on the other hand, we can decide too soon that, oh, we can't make it any simpler and it could be too much computation. So we're trying to balance these two in the problem formulation stage. That is why the stage is very critical. What we want to do is choose the simplest one that captures all the essential physics. That thought being very important, here is some more detail on what we mean. Overly complex formulation will make it difficult or impossible to compute. This is very real. It will be very difficult to debug, and it will also require a lot more resources than necessary. Too simple problem formulation, on the other hand, can completely lose the physics that we are actually interested in. Solve some other problem than is really intended. If we simplify it too much, it's not even addressing what we were hoping to address. So what is the right level of complexity? It captures the relevant physics or the experiment and is capable of being solved within a reasonable time. So here are two of the popular software that are used to solve the kinds of equations we are talking about. the point to make here is there's sometimes tendency to start implementing the model before the problem formulation is really complete and a lot of the important details are in. So we should not get into any software until we have completed the problem formulation and thus have the right equations to solve. Remember, we have to remember that the software are just equation solver. So we have to be first right in terms of the equations that we need to solve to the best of our knowledge before we get into. To conclude, problem solving is a critical step because it introduces errors and uncertainties, and it can be broken down into a number of steps. Those steps being goals, geometry, governing equations, boundary conditions, and material properties and other parameters. All of these topics will be addressed in individual videos that are the following videos in this series.